In Lesson 12, we'll be learning some more trig identities as well as graphs of logarithmic functions. Now, maybe you remember from advanced mathematics those key identities. They have those listed again there on page 96. You should write those down in your formula book that you're keeping and memorize those. Those are important to try to memorize. If you memorize those key identities, then you can derive all of the other ones from that. So in order to practice, let's just go ahead and work on double angle identities. And I want you to develop an identity for sine of 2a. And what you can do is base that on the sum and difference trig identities, those key identities. If you know those, then you should be able to figure out an identity for sine of 2a. And what you can do is just use the sum identity, sine of a plus b. That's equal to sine A cosine B plus cosine A sine B. Now, if we were trying to find sine of 2A, that's the same thing as saying sine of A plus A. So sine of A plus A, we could just say sine A cosine A plus cosine A sine A. And the order doesn't matter there. Sine times cosine or cosine times sine. So sine of 2A is equal to 2 sine A cosine A. So that's the double angle identity for sine of 2A. Let's do another problem. Let's develop an identity for cosine 2a. So we think about our key identities. Cosine of a plus b is what we would need here. And so that's going to be equal to cosine a cosine b minus sine a sine b. Now think about that. If we're doing that cosine a plus a or cosine 2a, we'd say cosine 2a is equal to cosine a or cosine squared a minus sine a or sine squared a. So there's an identity for cosine 2a. Now just think about this. Cosine squared plus sine squared is equal to 1. We already know that relationship. We could substitute that relationship in, or rearrange it and substitute it in for cosine squared and then for sine squared and come up with two more identities for cosine 2a. Just think about it. If we said cosine squared a equals 1 minus sine squared a, we could substitute 1 minus sine squared in for cosine squared, and cosine 2a is equal to 1 minus 2 sine squared a. Likewise, if we substituted in for sine squared, if we said sine squared equaled 1 minus cosine squared, we'd end up with cosine 2a is equal to 2 cosine squared a minus 1. So there we have three cosine identities. Just one sine double angle identity, but three cosine double angle identities. We used deductive reasoning to find some new rules. We started with key identities. Those were our fundamental rules here, and then we built on those to find some double angle identities. That's what deductive reasoning is about, finding new truths based on some truths that you've been given. Let's go ahead and do a practice problem, or another practice problem. This one says if sine of x equals 1/4, find cosine of 2x. Well, just think about that. That's a double angle identity we'd be dealing with because we have cosine of 2x Remember, there were three ways to write that identity, and one of those could be in terms of sine of x, right? 1 minus 2 sine squared x. So we know that sine of x is equal to 1/4. We can just say 1 minus 2 times 1/4 squared. So that equals 1 minus 2 times 1/16, which would just be 1 minus 1/8, which is 7/8. So that's what cosine of 2x would equal if sine of x is equal to 1/4. A pretty simple problem if you remember your double angle identities. Let's do a trig identity problem where we want to show the left side equals the right side. So on a problem like this, what we want to do is expand that left side out first. Get rid of that squared term there. And so we would have sine x minus cosine x times sine x minus cosine x. We remember on problems like this that we already know the answer. We already know the answer is going to be 1 minus sine 2x. We just need to get the left side to look like that. And so let's expand this out. Sine times sine would be sine squared. And then sine times minus cosine would be minus sine cosine. We'll have two of those, so we should say minus 2 sine x cosine x. And then we'll have a plus cosine squared x on the end. Now, hopefully you see you have a sine squared plus cosine squared. That equals 1. 1 minus 2 sine x cosine x. And then maybe you recognize that 2 sine x cosine x, that's the sine 2x double angle identity. And so we end up with 1 minus sine 2x. So we have shown that the left side does indeed equal the right side. If you write anything down in your formula book, write down the key identities on page 74. But you should be able to develop all of the double angle identities from those. Let's work on some identities for the tangent function now. Now, don't get the tangent function confused with when we're talking about derivatives and talking about finding the slope of a line that's tangent to a function. In mathematics, we have two different definitions for tangent. We talk about in trigonometry, tangent, that's the ratio of the opposite to the adjacent side in a right triangle. And then we also have tangent, meaning a line that touches at just one point. Here we want to talk about identities for the tangent function. And the best way to understand these is just to develop the identities for tangent a plus b and tangent a minus b based on our key identity. Let's just do a practice problem and identify or develop an identity for tangent a plus b. So just think about it. Tangent is sine over cosine. That's one of our key identities. Tangent theta equals sine over cosine. So we can say that tangent a plus b would be sine of a plus b over cosine of a plus b. Now we look at our key identities and break sine of a plus b and cosine of a plus b up. Sine of a plus b would just be sine a cosine b plus cosine a sine b. And then cosine a plus b is cosine a cosine b minus sine a sine b. Now, to develop this identity further, what we do is we want to get it all in terms of tangent if we can. And the accepted way to do this, I mean, there's more than one way we could do this. The standard way to do it is divide every term by the first term in the denominator. So this cosine A, cosine B, we divide everything by that. If we divide everything by it, we're not changing the value of this expression. We're just going to change the way it looks. So that means everything in the numerator is also going to be divided by cosine A, cosine B. Kind of running out of room over there on the right. But hopefully you get the idea there. So what's going to happen, cosine A, cosine B, that term on the denominator, that's going to equal 1. And there's nothing else we can cancel in the denominator. So let's just go ahead and rewrite this. So let's just think about that first term in the numerator. That's sine A, cosine B. And we can divide that by cosine A, cosine B. So the cosines would cancel there, and we'd have tangent A. And then if we look at the second term, cosine A sine B over cosine A cosine B, our cosine A's would cancel there, and we have plus a tangent B. The denominator will be 1 minus tangent A tangent B. So we have this all in terms of tangent now. So this is an identity for tangent A plus B. So that's an identity you should write down in your formula book to remember. And I'm not going to develop tangent A minus B, but it would be a similar process. You would use sine A minus B over cosine A minus B. Use the same format, break those up into those key identities, whatever sine A minus B and cosine A minus B are. Then you divide every term by that first term in the denominator. Let's apply what we learned here. Find the tangent of 105 degrees. Do that without using a calculator. So think about that. You could say that that equals tangent of 45 plus 60 degrees. And so then you would have tangent, just use your identity that you just did, tangent 45 plus tangent 60 over 1 minus tangent 45 times tangent 60. So tangent of 45 degrees would just equal 1, right? And then tangent of 60, that would be the square root of 3. So we have 1 plus the square root of 3 over 1 minus 1 times the square root of 3. So 1 minus square root of 3 is on the bottom there. We don't want a radical sign in the denominator, so we multiply above and below by the conjugate of the denominator, 1 plus the square root of 3. Our denominator, we end up with 1 minus 3, or a negative 2. And then in the numerator, we get 1 plus 2 times the square root of 3 plus 3, or 4 plus 2 times the square root of 3. And that can all just simplify to a minus 2 minus the square root of 3. So that's what the tangent of 105 degrees is equal to. We use the tangent A plus B identity to help us solve that problem. The goal here with these tangent identities is not really to memorize the tangent identities, but to use deductive reasoning. In other words, apply the key identities that you already know about to finding this new rule. That's the great thing about deductive reasoning. When you use it correctly, you don't have to remember quite as many things. We have identities for cosine and sine of 2a. Let's go ahead and develop an identity for tangent 2a. Well, we already know what tangent a plus b is, so we could just say tangent a plus a. We could just say tan a plus tan a instead of tan a plus tan b over 1 minus tan a times tan a.
And so we would just end up with 2 tan A, and that would be over 1 minus tan squared of A. And so there's our double angle identity for tangent 2A. It would be a great idea to memorize those double angle identities that they have listed on page 77 of your textbook. Trig identities can be very useful for simplifying different expressions that you may come across in calculus. Of course, you can always write them down in a formula notebook or refer back to this page if you need to, but if you have them memorized, that's one less step that you have to go and do. You can just pull from your memory and simplify the problem much quicker. Part C of this lesson is on half-angle identities. We can develop identities for cosine of x over 2 and sine of x over 2 using two of the double angle identities for cosine. So let's start with the one on the left here, and let's just rearrange that to say, or to solve for cosine squared. And so if we got cosine squared A by itself, we could see that that would rearrange to half plus half cosine of 2A. Now to make a half angle identity, what we do is we set A equal to x over 2. And so if we substitute that in and also take the square root of both sides, you could see that we would end up with cosine, placed A with x over 2, so we have cosine x over 2 is equal to plus or minus the square root of half plus half cosine x over 2. So there's the cosine half angle identity. And the sine half angle identity, you can see that would just, you follow the same procedure, set it equal to sine squared A and take the square root of both sides, and you end up with sine x over 2 equals plus or minus half cosine x instead of half plus half cosine x. And actually over here for the cosine one, we need to erase that, and we had that as x over 2. We need to change that to just cosine x, because 2a times x over 2, or substituting x over 2, and you have 2 times x over 2, the 2's cancel. You won't use these two identities quite as much as the others, but it would still be good to memorize both of them. Let's go on to part D and review graphs of log functions now. To review graphs of logarithmic functions, let's just graph a couple of functions here. Y equals 3 to the x and y equals log base 3 of x. And we'll graph them on the same Cartesian coordinate system. So let's just go ahead and make a Cartesian coordinate plane and put some tick marks on it. And we've been working with exponential functions, and we know that if we have a positive y equals positive 3 to the x, we know that that's going to go through 0, 1, and since the base is greater than 1, it will curve up and to the right. So we could put one more point on there when x is 1, y is 3. Put a dot right there, and we know it's going to curve up and to the right like that. So that's the graph of y equals 3 to the x. So we could just put 3 to the x next to it, because what we want to do is graph y equals log base 3 of x on this same Cartesian coordinate plane. We want to be able to distinguish between those two graphs. Now think about y equals log base 3 of x. We can't figure out the base 3 logarithm of any values that we might substitute in for x. So let's use our exponential form of that logarithmic relationship. We would just rewrite that as x is equal to 3 to the y. And do you see how that's similar to our exponential function, y equals 3 to the x, that we just graphed? It's just that the x and the y have traded places. To graph this, what we could do is just make an xy table, and normally what we do is y is our dependent variable, so we find some values for x to substitute in. In this case, x is considered the dependent variable. So we'll find some y values to substitute in. Let's just pick three easy ones, -1, 0, and 1. And think about what happens here when when y is -1, we'd have 3 to the -1, which is the same thing as 1 over 3. So that's what x would equal, is 1/3. When y is 0, we'd have 3 to the 0. Anything raised to the power of 0 is just equal to 1. So x would be 1 in that case. And then when y is 1, x is 3. So now we can go ahead and graph that. Our first ordered pair there would be to the right 1/3 and down -1. So estimate that, be about right there. The next one would be to the right 1, 0. So the exponential function went through 0, 1. Logarithmic functions go through 1, 0. And then one more point to the right 3 and up 1. Now we can go ahead and graph that. So you can see the similarities there in y equals 3 to the x, and then y equals log base 3 of x. They're basically symmetrical images of each other about a line y equals x. That dashed line I just drew there is the line y equals x. That green curve there, that's the y equals log base 3 of x. That's the graph of that function. So remember that pattern for a logarithmic function. Remember that shape. Remember also, to graph it, you can change it from logarithmic form to exponential form. Substitute a few values in to help you locate and identify where the curve will go. Let's have some practice graphing logarithmic functions on a graphing calculator, and let's graph this function, y equals log of absolute value of x. Your graphing calculator can graph base 10 and base e, or natural log, functions. So if you want to graph log absolute value of x, that's base 10 log of that, go to y1 equals and then hit log. Now to do the absolute value of x, you'll need to go to math, hit your math button, and then move over so that you are on number, N-U-M, and then you can press the number 1, and that's the absolute value. And so that will actually show up over here. You'll hit ABS, and the ABS will show up over here, and then you'll have parentheses, and you'll put your x in there, close parentheses, and then close the parentheses again for the whole function. Set your window up, hit graph, and you should come up with the graph that's shown here. Hopefully that makes sense to you. As this approaches 0, either from the left or from the right, the logarithm is undefined. Notice that it passes through that point right there, -1, 0, and then 1, 0. And we see that we have a pole or asymptote there at x equals 0. Okay, well that's all for lesson 12.